Really, all I want to do is a bit of an update on what was presented at our last partners meeting in Ottawa. And this is basically work by two of the postdocs who've been working on the Timmins area, and it's essentially Gaetan Lange's presentation, but a lot of the MT data is coming from work by Adamola, who's put all the data together into data models for MT and AMT. So really, just to give you an overview, it's focused on the Timmins area here. The Timmins area is on the western part of the Porcupine-Dester Fault, and it's one of the best endowed fault systems in the Abitibi, along with the Cadillac-Larder Lake deformation zone. Both of these have produced approximately 100 million ounces of gold over their history of the mining along those two areas. A lot of it for the Dester Porcupine has come from the Timmins Camp. So what we did is back in the mid-2000s, the Discover Abitibi research program did seismic lines through the Timmins Camp. Dave Snyder was involved in a lot of the interpretation of that. So we thought this was a good opportunity for basically going to an area where there was seismic to do some MT. So we did two approximately 100-kilometer lines north-south across the Timmins Camp. And Adamola is currently working on a manuscript to put all that data together with an interpretation of the crustal structure. But we also did some high-resolution AMT, and it wasn't funded by Metal Earth. It was basically funded by companies that were offered the opportunity to come alongside with us and to do AMT in areas that were of interest to them. So we had 4 companies join in, and the map here shows where we had the various areas of AMT done. The biggest area was an area that Newmont came along and wanted to do 150 stations, largely over the Timmins Camp. So that's there. Other areas, we had a nickel company that's exploring for nickel in mafic, ultramafic intrusions. Canada Nickel did a set of MT up in the north over the Crawford intrusion that they're currently exploring, and then another mafic, ultramafic intrusion in the northwest. And then we had 2 other companies, and this is in the Kamoskosia in the western part of the map, and a junior company, International Explorers and Prospectors, did essentially a transect across their ground in that area. And then in the south, on the west, what they call the Timmins West Gold Camp, Pan American Silver funded additional AMT lines down in this area. So what I'm going to show you is basically the area that we have the most data is probably the most illustrative of what the AMT can tell us with respect to patterns which relate to conductivity in the upper crust. AMT seems down to about 3 kilometers, and how it relates to gold mineralization. So this is essentially the Timmins Camp here. The gold deposits, I don't know if you can see them, but they're shown here in just the symbols. And so this is the area that's produced 70 million ounces of gold. And what we see here, this is the uppermost crustal slice of the AMT at about 200 meters. And we're seeing some patterns of high conductivity, or basically low resistivity. And there's some places that we're seeing concentrations or higher values. So this is a major fault that goes through the Timmins Camp, and pretty well all the major deposits are located north of that fault, and that's the Dester Porcupine Fault. There's a series of faults, less extensive faults, largely associated thrusts that are to the north, and a number of the gold deposits are associated with that. And we're starting to see, even at that crustal depth, a fairly shallow crustal depth, there is some responses. And as we go deeper, this is at about 600 meters, we're starting to see some trends develop, so going deeper into the crust. We see a fairly pronounced trend here in the north part. This is what they call the North Mine Trend. And it extends from the Bell Creek, which is a deposit that's currently being mined by Pan American. And then the Hoyle Pond deposit is a current mine that's being mined by Newmont. So there's definitely a correlation with this trend and also with some faults that are up along this trend as well. As we go further south, we start to see a trend that's developing along, but not all along it, but sort of locally along the Destor-Porcupine Fault. And then we're starting to see some trends developed around the Dome mine, which is a mine that produced about 15 million ounces. And then another trend that's immediately north, further west of that, in the area just north of the Destor-Porcupine Fault. This is about a kilometer. You're seeing the trend along the north trend where these deposits are located is actually becoming more conductive. And now we're seeing a new trend further to the north. There's not much work been done on that area, but it's an area that should receive more exploration just on the basis of the correlation. We're starting to see areas south of the Porcupine Destor, and these are likely where we have graphitic argillites within those rock packages. And this one, which is north of the Dome, is now becoming arcuate and trending off to the northeast. And that is an area where we have, they have basically done a lot of drilling here, and there's a graphitic unit between two major assemblages in the camp, the Tisdale Volcanics, which hosts a lot of the gold, and the Porcupine sediments, which sit on top of it. So in places there's 100 meters of graphite there, so that explains pretty well what that conductor is. And then this one that was north of the Porcupine Destor in here is extending up into the two biggest deposits in the Timmins camp, the Hollinger and McIntyre. Now we're going to about 1.5 kilometers. These trends are continuing. This one is blooming, the one to the north that hasn't really been explored that much. We're seeing this trend that's likely related to graphite extending further to the north. We're seeing a new trend which is following along the Burroughs-Benedict Fault. Not sure exactly what that is, but there's some suggestion that these, at depth, these conductive trends are being folded. And we're seeing, again, now this trend that was around Hollinger-McIntyre is moving a little further to the north. So now I'm going to show you sections through the various parts of the camp from the model, just to show you what these anomalies look like at depth. And so starting from the west, we're going from AA prime, and to the east, we're going from DD prime, so 4 sections. In the farthest north, we see the trend that's very shallowly dipping, not sure why it is. It extends from where we have the thick graphitic unit in what's called the Chaorium syncline in here, and it extends right underneath the two deposits, the Hollinger-McIntyre. And then this one goes right through basically the Dome area, and this is the Porcupine Destor Fault, but it's also that area where we have thick graphitic sediments, and it may relate to that. It is also dipping fairly shallowly to the north. What we're starting to see now in the north is another trend, which is quite pronounced here, quite a large area of conductivity, down to about 1 kilometer or so, and that's the westernmost part of this north trend. As we go further to the east, This goes through the Bell Creek mine, currently producing mine. We're seeing some conductivity south of the Desert Porcupine. And as I mentioned, there are graphitic units at the contact between the volcanics and the sediments in that area might reflect that. A small conductive anomaly under the Porcupine Desert, and where we're seeing the conductive anomaly along the Porcupine Desert, it doesn't go down more than a couple hundred meters, so that's probably reflecting that. We have one that occurs here at more or less just north of the Porcupine Desert, and then this big one, C5, which is underneath the Bell Creek mine. And then again, the final one to the east, you're seeing a conductor basically at the Pamour mine, which is very close to the Porcupine Desert fault, and quite a bit of resistivity here where this is dominantly just grey-wacky type sediments in the Porcupine. And then another substantial conductor which connects with all these ones. And then further to the north, you're seeing that deeper connector which hasn't been investigated. So what Gaetan did is he wanted to figure out what could be possibly these conductive anomalies might possibly related to. So we've seen that repetitively when we've done AMT. We see conductors or low resistivity zones that come fairly broad sweeps within the mid and sometimes the lower crust, and then fingers coming up into the upper crust. Well, we can't go down and figure what they're related to at 5 to 10 kilometers, but we can, in an area like this where we have AMT, explore them at areas where we can access the rock type. So what we decided to do here was to basically, Gaetan, and I helped him out last summer, was go to the companies where we could access drill core and sample rock types from fences or cross sections across the deposits. So the idea here was to test what could possibly be the cause of these conductive anomalies. So in the lower left here, we see a typical diagram showing the responses of typical rock types for conductivity and resistivity, and we see the ones that are most conductive are massive sulfides, no surprise there, and then followed by graphites. A little bit more in mafic and ultramafic rocks, and particularly where they get altered, and less so in felsic rocks. And then we have things that are not likely around the Archean, like salt water and things like that. So what Gaetan did is he produced maps showing where we knew we had different types of phenomena that could or could not be related to these conductive anomalies. And so up in the upper right here, this is showing in the red lines. I don't know how well you can see these or not, but these are the areas where we know we have quartz carbonate gold veins. So there's a fairly good correspondence, particularly in this north trend. Some down here, down in the south as well. So there's some possibility it relates to that. This is where we know there are thick sequences of graphite shown in the red lines here, and there's a pretty good correlation with that. Some up in and around Horapan here. This is this thick unit of graphitic argillite at the contact between the Tisdale and the Porcupine, and similar here. So we're seeing some correlation, although they're skewed off, particularly this one that's south of Holland or McIntyre. And here, I don't know if you could see it, but there are lines, light red lines that show where we have ultramafic rocks, because we wanted to test that. We know that along the Porcupine Desert, particularly in this area here, there are a lot of altered talc chlorite schists which are derived from ultramafic rocks. So those are the three possibilities that might be responsible for these anomalies. So what we then did, I worked with Gaetan, we collected 250 rock samples from all these areas where we had, we knew that there were conductive anomalies from the AMT model. And we had those samples sent to for analyses, 250 to the Petrophysics Laboratory at the Geological Survey of Canada. And each sample was analyzed for resistivity, chargeability, porosity, magnetic susceptibility, and density. So I want to show you some of the results of that. So this is a chart that shows these are the different rock types. This is resistivity. So these are the conductive ones down here, low resistivity. And just for using the density, we did a plot of resistivity against density. These are the mineralized samples. They have lots of sulfides, so they're the most dense. But we see also the graphitic samples with the triangles are down here, and some of the ultramafic samples. So these are the ones that are the most conductive rocks that we were able to determine from this 250 samples. Here showing you the same thing, resistivity on the horizontal and chargeability. So now we're really low resistivity, high chargeability. It's the same thing, really. These are the ones that are most likely responsible for conductivity with respect to AMT. So I'm just showing you now what's the response of different rock types to with the respect to their resistivity values. So we show you up in the top chart here, the top graph, these are ultramafic rocks. So the unaltered ultramafic rocks, there's lots of those within the Tisdale. Those show are the most resistive. So they're least conductive. Altered ones, however, are starting to show that they have lower responses for resistivity. Maybe a little more conductive, but not superconductive. Same thing for mafic volcanic rocks. Dark green are relatively unaltered. Light greens are the altered. So a little bit more, not as much as ultramafic, but not something that's likely to cause a major AMT response. And then felsic, these are quartz porphyry intrusions. The reverse, the unaltered ones are slightly more resistive than the fresh ones. Not sure why. Now we're looking down at the graphitic rocks in the black here, and those are the ones where we're seeing a large range of resistivity values, but down to low values. And so I'm going to show you each one what the responses were. So first of all, we're going to look at one that goes through Bell Creek, and basically starting in the vicinity of the mine and working south. So here's the basically the fence where it was not one hole, there was probably 4 or 5 that were involved that we put together. And it shows you the blues are the various parts of the Tisdale, mafic volcanic dominantly, but some ultramafic shown in a darker blue. And then the browns are the porcupine sediments. So those are the gray wackies. So where you see, and also on that, so here you have basically the resistivity values. So the ones that are on the extreme left of that diagram are highly conductive, are low resistivity, and contrasting it with chargeability. And so we wanted to look at where we would see the response of resistivity and chargeability for the different rock units as we went through these holes. And also we had the assay values from the logs, and so Gaetan put these in here as well. So this is starting up in the northern part at the mine, essentially, where they're producing their ore. And so we've seen basically the little red arrows. I don't know if you could see them. Those are where we actually collected samples from ore zones, and we could see fairly good resistivity, low resistivity in some, and high chargeability. So that's a likely place where we could see a good AMT response. Going through this Tisdale to the south, Tisdale itself, the mafic volcanics, not much. But then we hit a graphitic fault zone at the contact, and that again gave us low resistivity, high chargeability, so a good conductor. Another one within the sediments, and so on and so forth, down to another contact. This Tisdale porcupine is folded back and forth in this area, so that's why we're seeing the repetition. This is a Hoyle Pond mine, and so we put again a fence basically right through that whole stratigraphy across the Tisdale. Here you're seeing the Hershey ultramafic unit right in the central part of the Tisdale. It's essentially an anticline with the ultramafic units in the core, and again the contact to the porcupine sediments to the north, and the contact with the porcupine sediments to the south. So we're seeing the responses where we saw graphitic fault systems. These are what they call gray zones, here and here and down in here. There, these are basically zones which are basalt, but it has a gray color, a moderate amount of sulfides and graphite. So some of those show up as conductors as well. This is the same basically trend, but further off to the east, about 4 or 5 kilometers east of Hoyle Pond. There are mineralized zones within the same stratigraphy there, so we did the same sort of thing, running across the Tisdale part of it, ultramafics within it. Some of the gray zones we're seeing in here, not any appreciable response, but some of the graphitic fault zones, we definitely had responses to those. So we're seeing a pattern here. We're definitely getting good responses where we see graphitic fault zones. This is around the Halnor deposit, and it's basically all within the Tisdale. We're seeing some gray zones here. Some of them have a little bit of response in the graphitic faults as well. And then lastly, through the Pamor deposit, a little bit offset of where the main mineralization was, a little off to the east, but again, going from the Porcupine into the Tisdale and then finally into the Temiskaming here, and you're seeing the same sort of patterns there. So basically, the summary of all this is that the conductive anomalies are spatially associated with known mineral deposits. That's pretty clear. Large-scale east-west trending conductive anomalies through the Hoyle Pond, Owl Creek, and Bell Creek. That's that north trend. Another conductive anomaly lines up well with the Porcupine Jester as it extends from east to west, especially at depth at about 250 meters to about 600 meters, so it's not going beyond that depth. The Dome and Hollinger deposit relate to folded conductive anomalies, folded graphitic layers of the crust. So that's basically the southern termination of that graphitic layer. That's basically where we're finding the Dome. And the Hollinger is related to another anomaly which appears to be not too far away from where the larger graphitic unit is. So it appears that we can conclude that the conductive anomalies highlighted by AMT are likely related to graphitic faults occurring in the Timmins Camp. These faults are spatially associated with high grades of gold and altered and mineralized mafic volcanic rocks. The gray zones are also characterized by lower values of electrical resistivity and are basically a bit lower grade than the graphitic fault zones, which the gray zones are strata parallel, and they appear to be earlier fault zones within the stratigraphy, parallel to the stratigraphy. Some of the graphitic fault zones cross-cut, so this appear to be later structures. And so that's it. That's from GATAS, so I can try to answer anything.